In this video, we're going to look at solving systems of differential equations with a repeated eigenvalue. So the first thing I'm going to do is give you a kind of a generic what the solution would look like, and then we'll do an example of how to get there. So a solution to a system that has repeated eigenvalues. Now this is going to look really familiar at first. So C1, then the eigenvector, then e to the eigenvalue times t. So all of that is pretty normal. Then we've got this C2. Now that second constant is going to be multiplied by a couple of things. It's going to be multiplied like you would think intuitively from repeated root problems, is that you'd multiply by t and then have your eigenvector and then e to the lambda t. But just that causes issues, and so we need another vector. We're going to call it the p vector, and that vector is also going to be multiplied by e to the lambda t. So C2 has two pieces that go with it. One with the t multiplied by the eigenvector, and then this other vector in there. So let me just at least a little bit give you a bit of a reason why we need this other vector in there. So imagine that you've got your initial condition where t is equal to 0. When you plug that in and t is equal to 0, that takes out this term. So notice that if that is taken out and that other vector and term is not there, then it's impossible to solve for C2. So you actually need this other associated vector in there to be able to solve this system. And even if you just want to try it, plug it into a differential equation and see if it works, a solution like this, see if it works, you'll find that it doesn't. You need this other vector. So let's move on and look at an example. All right, so here is our example, and just notice that we have these values in front of x and y. That's going to give our matrix A. So when we go to find the eigenvalues, we're going to do the determinant of A minus lambda I. So that would be a 1, that would be a negative 4, then we'd do negative 3 minus lambda. So A minus lambda I. So the determinant of this is equal to, what have we got here? We've got a lambda squared. Then we've got a negative 3 times a negative lambda, that's a positive 3, and a negative lambda times a negative 7, it's a positive 7, so that looks like that's a plus 10 lambda. And then we've got a 21, and then minus a negative, so that's a plus 4, it looks like a plus 25. And then this can be factored into lambda plus 5 squared. So that means that our eigenvalue is 5. And that is after we set it equal to 0. So now for that eigenvalue of 5, I'm going to plug that into this matrix. So I've got negative 7 minus 5, that's a negative 12. Then 1. Then negative 4, and then negative 3. I did something wrong. This is not working out well. Oh, hey, let's make that a negative 5, huh? I just noticed there's no symmetry in here. That can't work. Okay, so let's try again. Negative 5. Negative 7 minus a negative 5, that's a negative 2. Negative 2, and then a 1, and then a negative 4, and then a negative 3 minus a negative 5, so that's plus a 5, that's a 2. That looks way better. Okay, so there's my A minus lambda I. I'm going to multiply that by x, y, set it equal to 0, and I can see that a vector that would work is going to be 2 and 1. Because if I multiply negative 2 by 2, I get negative 4. Did I just do that wrong? Yep. See, good thing I'm checking these things. All right, let's try this again. Erase and put in, what is going to work here? 1, 2, huh? I think I just had it backwards. Okay, let's try again. if I multiply -2 times 1, I get -2, and then 2 times 2 is +2, and add those together and you get 0. -4 times 1 is -4, 2 times 2 is 4, add those together, you get 0. Okay, so there's our eigenvalue and eigenvector. Now, here's where we're going to do this other vector. It's not even an eigenvector, it's just an associated vector. Okay, so to find this vector, we are going to take A minus lambda I. We're going to find that vector P, and we're going to do that by, instead of setting this equal to 0 like we do the eigenvector, we're going to set it equal to the eigenvector. All right, so A minus lambda I from the previous page was -2, -4, 2. I'm going to multiply this by the P vector. I don't know, let's call these components P1 and P2. And set it equal to the eigenvector 1, 2. So when I multiply this out, I've got -2p1 plus p2 has to equal 1. And -4p1 plus 2p2 has to equal 2. And if you look at these two equations, what I usually try to do is set one of them equal to 0. And notice that if you set P1 equal to 0, that P2 can equal 1. And that would work because 1 is equal to 1, and then 1 times 2 is 2, that's equal to 2. All right, so there's my P vector. So now I can put the entire solution together. So I've got C1 eigenvector e to the eigenvalue times t plus C2 times t times the eigenvector times e to the eigenvalue. And then we have this other vector times that e to the eigenvector multiplied by t. All right, let's put in those initial conditions. So I'm going to plug in 0. And if I plug in 0, the e's go away. So I've got C1 times 1, 2 plus C2 times, notice that if you plug in 0, that first component multiplied by C2, that first term goes away because it's got a t in it, so that's 0. It leaves that P vector. And if you look back to the first page on the initial conditions, we said that the initial conditions were -1, 0. So if I look at all of the things on the top here, I've got C1, C2 times 0, and a -1. So that would be C1 and then C2 times 0. So C1 is going to be -1. And then I've got 2C1 plus C2 is equal to 0. Plug in -1, gives me -2. Add that to the other side. So C2 is going to be 2. So now, if I say that C1 is -1 and C2 is 2, I can now plug those in and then write this solution as one big vector. So, and I'm going to do, maybe what I'll do is do everything on the top first, and then I'll look at everything on the bottom. So on the top, I've got -1 times 1 times e. So that would be a negative e to the -5t. Then I've got plus C2 is 2. So 2 times 1 is 2t e to the -5t. And then I've got a 0. On the bottom, I've got -2 e to the -5t plus 2 times 2 is 4t e to the -5t. And then I also have 2 times 1 e to the -5t. So that's another 2 times 1, that's a positive. So that means that that guy is not there because we've got a -2 and a +2. So I'm going to erase that term. And there's our solution. All right, So again, the key on all of this is this extra vector p. And one thing that I do want to stress in finding it is that this is a minus lambda I. A common mistake is to use a right there instead of a minus lambda I, and you won't get a correct vector for both components. So make sure you use a minus lambda I there.